Hello, welcome to this 14th lecture session of Database Management Systems. In the previous session, we discussed about the basics of indexing, which is a popular technique for fast retrieval of the records from the database. We have seen what is indexing, what is a primary index, what is secondary index, sparse and then dense indexing, and at the end of the session we have seen some examples related to primary indexing and then multi-level indexing. If we look at multi-level indexing, it is like this. We have data blocks in the data file, then we have multiple levels of indexing in the structure. This is first level indexing. This first level indexing blocks will point to the data blocks in the next level, and then we have second level indexing where the blocks, indexing blocks will point to the next level indexing blocks which are available at level 1 in this example, and we have the third level and wherein we have only one block available, and that is called as the master block, or which is called as the top level. Whenever we are making an insertion or whenever we are making a search for a given record, the search always starts from the master block. We have only one block at the top level, and hence it can be viewed as a tree. It is called as a multi-level indexing, and this is the root of the tree, and this is the first level of the tree, this is the second level, so on and so forth. Okay, so when you have this kind of thing, search always starts from the master block, and then from here we find out, depending on the keys available at the entries and following the pointer, we reach the next level block, and from there we reach the next level block, and which actually takes us to the data block which contains the required record. Hence, if I have 3 levels in my indexing structure in the multi-level indexing, the number of block accesses required are 1 access at each level, that is 3, plus 1 access for the actual data block at in the file. So that is 3 plus 1, that is going to be 4. This is multi-level indexing. Now in this session we will discuss what is tree indexing, what is B plus tree, what is B tree, and inserting and then deleting keys from B plus trees, constructing a B plus tree, and then designing a B plus tree node structure. All these things we will discuss in this 14th lecture session. First, tree indexing, adopting tree structure for implementing indexes. A tree consists of nodes and leaves. The number of arcs from a node in the tree to the root is known as the path length. The height of non-empty tree is equal to maximum level of the node in a tree. For empty tree, the height is considered to be 0. And we have binary trees. Each node has maximum 2 children, left and right children. Hence, at ith level, the number of nodes present in the tree are 2 to the power of I minus 1. That is, the root level is considered to be at level 1. This is level 1, and then this is level 2. And then if I want to know the nodes at level 2, then it is going to be 2 to the power of 2 minus 1, which is 2 to the power of 1, which is equal to 2. Okay, and what is a binary complete binary tree? All nodes excepting at last level are present in the tree. That is, if you look at this, this is a binary tree which has 4 levels. If you carefully observe, the full number of nodes which are designated or which are to be there at each level, they are there excepting the last level. Hence, we call it as a complete binary tree. Binary search trees, for each node in the tree, all values stored in its left subtree are less than the value stored in the node, and all values stored in the right subtree are greater than the value stored in the node. For example, if I have some value, key value 78 here, and then all values in this left subtree will be less than 78, and all values which are in the right subtree of this will be greater than 78. This is called as a binary search tree. Then multi-level search tree of order M, or M-way search tree. What is this? Each node has M children and M minus 1 keys. This is very, very important for a M-way search tree. If a tree has 15 children, then it can accommodate 15 minus 1, that is 14 keys. If it has M children, it has M minus 1 keys. Keys in each node are in a particular ascending order. If you look at this, the node structure looks like this, and this is the pointer to the child, and this is the next pointer to the child, so on and so forth. So each of these pointers, they point to the subtree or some other node of the tree, child node of the tree. Now these are the keys, key 1, key 2, key 3 and then key 4. I have 5 pointers here, hence the number of keys possible are 5 minus 1, that is 4. Hence I have 4 keys, and if you look at the values of the keys, they are in a particular order, they are in a ascending order. For this example, the number of children m is equals to 5, that is called as the order of the tree, and number of keys are m minus 1, which is 5 minus 1 equal to 4. B plus trees, it is a multi-level search tree used to implement dynamic multi-level indexing. We have seen in the previous discussion, we have seen what is a multi-level index, which looks like a tree. The structure looks like a tree. Now, what kind of tree data structures can be used to implement that multi-level indexing? B plus tree is the most efficient and then effective way of implementing the multi-level indexing. The primary disadvantage of implementing multi-level indexes is that the performance degrades as the file grows. That is, lot of insertions and then deletions, then you need to manually handle them at the indexing structure, and it can be remedied by reorganization, but frequent reorganization of the structure is not advisable. But B plus tree is the best suited for multi-level indexing of files because it is dynamic. That is, when you insert a key or when you delete a key, automatically the reorganization or adjustment automatically takes place. Hence it is going to be more dynamic and then more efficient way of implementing multi-level indexes. And what is a B plus tree structure? B plus tree of order P, it is a balanced tree. That means all leaves are at same level, then it is called as a balanced tree. Okay, it is not the case that for some subtrees the leaves are at some level, and for some other subtree it is at some higher level or lower level. That is not the case, and all leaves in the tree, they will be at same level. It is called as a balanced tree. Hence B plus tree is a balanced tree, and each internal node has the structure or the form which is given here. And if you look at this, here m is equals to 5 because the order P is equals to 5 because it has the maximum number of children a internal node can have is 5. Now if it has 5 children, that is 5 pointers pointing to the subtrees, how many keys are possible? 5 minus 1, which is equal to 4. Hence I find 4 keys in each node where they are actually placed in a particular order, in a ascending order, and it is also a M-way search tree. B plus tree is a kind of M-way search tree. And if you look at the other important features of B plus tree of order P, within each internal node K1 is always less than K2. That means they are in a particular ascending order. P1, P2, so on and so forth, they are called as the tree pointers which point to the next level node. K1, K2, K3, they are the key values which are in ascending order from left to right. Each internal node has at most P. For a B plus tree of order P, each internal node has at most P, which is called as the order, P number of pointers or pointers to the child nodes. Each internal node except the root node has at least how many? So what is the minimum? If the order is P, what is the minimum number of pointers an internal node can have? It is P by 2 seal value. In this example, since I have 5, P is equals to 5, so the minimum number of pointers an internal node can have is 5 divided by 2 seal value, which is going to be 3. And there is an exception for the root. Root has at least 2 pointers. Okay, sometimes root can have only 2 pointers independent of this particular specific rule. An internal node with q pointers has q minus 1 field values or keys. That is obvious because it is a M-way search tree. All record pointers are available at leaf node only. The pointers which are pointing to the actual records which contain the key value are actually available at the leaf level. No intermediate node will have a pointer to the actual record. Once we get a key value at a leaf node, from there accessing next value in sequence is easy because all keys at leaf level are in ascending order. But suppose if this is the root and these are the next level, then this is the leaf. Let us assume that this is the leaf. In leaf, k, and then immediately k is equals to 18, there is a pointer which points to this. Then k is equals to 25 and there is a pointer which points to this. Similarly, there will be 35 which points to the record. That means once you reach the leaf level, and if I have accessed 25, to access the next record with the next key value, I can follow the key which follow the pointer which is connected to the next node at the leaf level. Hence, once I reach the leaf level node, from there accessing next value in sequence is easy, because all keys at leaf level are in a particular order, they are in a particular ascending order. Hence, once I reach a key value at the leaf level, then I can easily access the next value in sequence by following a pointer available at the leaf level. The example is given here. This is a B plus tree of order 3, and I say that P is equals to 3. Then if such is the case, what is the maximum number of pointers at internal node is equals to P, that it is equal to 3. What is the minimum number? This is nothing but 3 by 2 seal value, which is going to be 2. That means any internal node must have at least 2 pointers, and then it must have 3 pointers. And when it has 3 pointers maximum, what is the number of keys possible maximum? Only 2 keys are possible. And if it has minimum 2 pointers, then how many keys are possible? Minimum 1 key must be there at the intermediate level or internal node. There is an exception for the leaf level nodes, and in this case we define the maximum number of records or maximum number of keys a leaf level node can have. In this case, P leaf, we call it as P leaf, is equals to 2. That means it can have maximum 2 keys, and then along with the key value there will be a pointer like this which is pointing to the location of the record where that record contains the specified key value mentioned. So this is going to be the typical B plus tree structure. This is root, and any internal node, if P is equals to 3, must have maximum 3, minimum 2 pointers, and then maximum 3 pointers at internal node, and then maximum 2 number of keys, and minimum 2 pointers, and then minimum 1 key should be there at internal node. That is, if you carefully observe in the B plus tree, suppose if I am searching for a record with key value 6, let us assume like this. I start my search with the root, and 6 is definitely less than 17. That's why I take this path, and then 6 is greater than 5, less than 14. I take this path, I reach the leaf level. But unfortunately at leaf level I don't find any entry with key value 6. Hence my search is a failure case. And if at all I am searching for some record with value 4, I start my search here. 4 is less than 17. I reach this internal block, and then 4 is less than 5. I take this path, and then fortunately I find a record, I find a key value with 4, and then immediately next to that I have a pointer, record pointer, which will give me the location of that record containing key value 4. In this case it is a successful search. That means in a B plus tree, whether your search is successful or a failed search, and you will only declare that or know that only after reaching the leaf level. When you are at intermediate levels, you may not be knowing whether your search is successful or a failed search. Hence, you can find a record pointer only at the leaf level. That is the basic characteristic of B plus trees. Then we have another kind of tree, that is B tree, which is also like B plus tree only, and it is a M-way search tree. The only difference is the intermediate nodes also can have pointers to the required records. For example, look at this. This represents a B plus tree, and this is going to be the node structure for a B plus tree. And you have a pointer pointing to the tree node, and then you have a key, and immediately next to that there is a pointer to the record which contains key value k1. Then you have a tree pointer, then there is a key k2, and immediately there is a pointer which is pointing to the record with that data value. Then I have P3, so on and so forth. That means this is a typical node structure for internal nodes or intermediate node, and it clearly says that at intermediate node itself you can find record pointers, and if the key for which you are searching is matching with the key available in some internal node, immediately next to that you can find a pointer which will take you to the location which contains the record with the given key value. For example, it is like this. So this is a internal node. I have a pointer pointing to the next level, and this is a pointer pointing to the next level node, and then this is a tree pointer points to next level node. And then if I am making a search for a record with key value 3, I will, let us assume that this is the root, and then I will start my search here, and 3 is less than 5, hence it is not matching with this key value, and I need to follow this pointer. After reaching here, I look for the key value, entries with that key value. Yes, there is an entry with key value 3. Immediately next to that you will find a record that will take me to the, of course in this example consider this as the leaf node, and I immediately get a pointer to the record. But suppose, let us assume that I am making a search for a record with value 5, and I start my search here, and there is a key value in this node itself which is matching with the required key value, and next to that there is a record pointer which will take me to that location where I can get that record. Hence the difference between a B tree and B plus tree is that in a B plus tree you can find record pointers only at the leaf level, wherein if it is a B tree you can find record pointers even at intermediate level itself or at the root level itself if you are lucky. So hence the success, declaring to find whether your search is success, you need not reach the leaf level in case of B trees. That is, you may declare that if you are lucky enough you may find your key matching with the key value available at root node itself. Okay, whereas the failure can be determined or declared only after reaching the leaf level, whereas in case of B plus trees the failure or success can be known only after reaching the leaf level. That is the difference between a B tree and then B plus tree. Now let us focus more on B plus trees because they are the most popular data structures used for implementing multi-level indexing. In a B plus tree, record pointer for a record with given key can be found only at the leaf level. That is very important. But if it is in case of B tree, it can happen at intermediate node also. Hence in B plus tree search, success or failure can be declared only after reaching leaf level, whereas in B tree search can be successful at intermediate node level itself. On failure we reach the leaf level in both the cases, whether it is a B plus tree or B tree. If it is a failure case, we must have reached the leaf level. Now let us have a look at some example wherein we will get better understanding about how insertions and deletions take place in a B plus tree. Here a problem is given: construct a B plus tree with given specifications. The order of the tree is P, that is the maximum number of pointers in a internal node can be 3, and P leaf is equals to 2, meaning that the leaf node can accommodate only 3 keys. The tree should be such that all the key values, suppose if you take this as the node, if this is a key, all the key values, the tree should be such that all the keys in the subtree pointed by a pointer which is preceding the key must be equal to or less than the key value, and all the keys in the subtree pointed by a pointer which is succeeding the key must be greater than the key value. For instance, if you take this, if I have 20 here and then if I have 75 here, and then this is a pointer pointing to this subtree, and key values in this subtree must be less than 20 or equal to 20, and key values in this subtree must be greater than 20 and less than or equal to 75, and the key values in this subtree must be greater than 75. That has been stated here. And insert the following keys in the same order: insert 56 first, then 22, 78, 42, 102, 90, 96 and 35. Show how we need to show how the tree will expand after each insertion and the final tree should be showed or displayed. And once the tree construction is over by inserting these key values, our next job or next thing that need to be done is delete the key value 56, 46 and 22 in the same order from the tree. First inserting these values and then deleting these values from the tree. That is the problem given. Okay. This gives the keys that need to be inserted and in the same order, that must be inserted in the same order. P, which is known as the order of the B plus tree, is equals to 3. That means if you look at any internal node, it can have maximum 3 pointers, and if it is maximum 3 pointers, what is the maximum number of keys in any internal node? Only 2, that is 1 less than the number of pointers. And what is P leaf? If you look at any leaf level node, it can have only 2 keys, and then along with the key there will be a pointer to the record. Similarly, what is the minimum number of pointers that are possible in a B plus tree with order 3? It is 3 by 2 seal value. Hence the minimum number of pointers that must occur in any internal node is 2. If the minimum is 2 pointers, what is the minimum number of keys? It is exactly 1 less than the number of keys. Hence the minimum is 1. Okay, so that is the specification for the given B plus tree. Then we will start inserting 56. When I insert 56, I have only the leaf node, and that itself becomes the root node as well. So I have inserted 56, and then when I insert 22, since a leaf node can accommodate 2 keys, there is a space available and I can insert 22 here, but the values should be in a particular order. They must be in a ascending order, and put 56 here and then put 22 here. After inserting 56 and 22, this is the structure of the tree. It has only one node. Now when I am trying to insert 78, then in the leaf level node I have 22 and 56, but if I try to insert 78, then there is no room. It is a overflow condition because a leaf node can accommodate only 2 keys. Now what should I do? When there is a overflow, the height of the tree, I need to expand the height of the tree. So that's why when this is the situation, which node should be taken to the next level, next higher level? That to find out that 22, 56, the next key that is to be inserted where I found overflow is 78. Take the middle one to the next level, that is 56 to the next level. That is what I have done here. So 56 will go to the next level, and the whatever is the key value which is less than or equal to 56 will be pointed by the left child, and the greater than 56 is pointed by the right child. Hence 22 and 56 will be there in this leaf, and then 78 will be there in this leaf. And at every point of time when you make a insertion or deletion, you must be very, very careful whether you are maintaining the specifications or the rules laid down for that particular B tree or not. That is the minimum number of keys, minimum pointers, maximum pointers, whether it is satisfied or not. That need to be kept in mind while manipulating or working on this tree. Okay, so far it is good. After inserting 78, this is the structure of the tree. Then when I am trying to insert 42, where 42 should go, and to find out, to identify that 42 is less than 56, I have to take this. I have reached the leaf level, but there is only one node available and it is already full. There are 2 keys available. I cannot accommodate the third one. So if you write this in a particular order, 22, 42 and 56, which is the middle one, 42. Take it to the next level and check whether you can accommodate that in the next level or not, next higher level or not. So what is the maximum number of keys possible in a internal node? Maximum 2 keys are possible. There exists only 1 key. Hence I can accommodate 42 there in the next level. Hence in that node insert 42, 56 anyway there, and this pointer will take you to the leaf node where the key values are less than or equal to 42, and this pointer will take you to the leaf node where the values are greater than 42 and less than or equal to 56, and this is greater than 56. Now if you look at this, it is satisfying the conditions that have been laid down for the given B plus tree. And now when I am inserting 102, and always when I am trying to insert something, my search for the appropriate location should always start from the root, and 102 is greater than 56, hence I need to follow this pointer, and in that if you carefully observe, it can accommodate 2 keys, but there is only one key value, that is 72 available. I can happily insert the key value 102 into this bucket, there is no problem. Now when I try to insert 90, where 90 should go? 90 is greater than 56, I will go here, and 90 should get into this leaf bucket, but unfortunately there is no space available, it is already full. Now write the sequence of the new key value and the existing key values in ascending order: 78, 90 and 102. Which is the middle value? 90 is the middle value. Now take 90 to the next level, next higher level, and try whether you can accommodate it there or not. If it is not possible, you need to create one more level. There is an overflow. So whenever there is a key, and then if you are unable to insert that, and then you find the bucket is full, then it is called as a overflow condition. Whenever overflow condition occurs, take one of the keys and then try to accommodate that in the next higher level, and if it is not possible, then you need to go to the next level, and you exhaust all the possibilities, and then you reach the root level. Then it is certain that you are going to increase the height of the B plus tree, and in this case 90 cannot be accommodated here. I will try to accommodate 90 here. If I insert 90 here, there will be 3 keys, and according to the rule, the maximum number of keys that can be possible in any node is maximum 2, hence it is not possible. 90 cannot be accommodated here. So hence again, now I need to increase the level. Now to do that, write the sequence 42, 56 and then 90, which is the middle one, 56. Take 56 to the next level. There exists no such level, so this is whatever is the node that is at the root level. Hence now I need to create one more level and then create one more node and insert 56 there. 56 has come here, 42 will remain as it is, and then 90 will be here, and then whatever is this pointer, that will take me to the leaf bucket where I have 22 and 42. This one take me to the value 56, and then if I take this path, it is 90 here, and whatever is less than or equal to 90, which is on the left side, and greater than 90, which is on the right side. This is how I can insert values into the buckets. Suppose now it is time to insert 96, and I need to start my search for the location at the root level. 96 is greater than 56, go to this bucket. 96 is greater than this key value 90, go to this bucket, and 96 there is a space available, I can accommodate 96. So hence I can insert 96 there. Yeah, 96 can be accommodated there. Yeah, 96 will come here, and then 102 should be here. This is how we can do that, and this is how we insert values into the tree. At every point of time, we need to be very careful about whether the min and max keys and pointers condition is satisfied for the tree or not. And once I insert all the keys, then this is going to be the final shape of the tree. Okay, I have 1, 2, 3, 4, 5, 6, 7, 8 keys available. So I have 1, 2, 3, 4, 5, 6, 7. Of course, 96 should be here, and then 102 should be here. And then if you look at the leaf level, all the record pointers will be available at the leaf level, and the key values at the leaf level will be in a particular order. Okay, so there will be a pointer which is pointing to the next leaf level bucket. Hence, once I have accessed the leaf node, it is easy for me to access the next sequence, next key value in the sequence by following this pointer. Now let us have a look at how to manage the deletion operations. Suppose let us assume that this is actually 96 and 102, and if I am trying to delete 56, what will happen? There should not be a underflow condition. When you insert, keep on inserting, you may encounter overflow condition, and when you try to delete, you may encounter underflow condition. So now I will, in this tree, from this tree, I will try to delete the key value 56. The key value 56 is available, and in this leaf node the only one key is available, and if I delete that key, what happens? That results in underflow for that particular leaf node. According to the rule, the leaf node must have at least one key value and then maximum two key values, that is the p leaf order of the tree. And now when I delete 56, that results in underflow. So what I can do? I can borrow some keys from the next left hand side bucket and then readjust or reorganize. What I am doing here? I am borrowing 42 and then I am eliminating this, and in this node now there is only one key available, that is 35, and this pointer, right hand pointer, will have a pointer to this bucket and which contains 42, and here 22 and then 35. And since 56 is not there, now I will take that 42 to the next level, because 56 is not there, this will not be there. I am making it 42, and 35 is less than 42, there is no problem, and 90 is greater than 42, there is no problem, and this is after deleting 56. Now it is asked to delete 46. In fact, there is no such key exists in the tree, hence the deletion of 46 is not possible. And when I am trying to delete 22 from this tree, the 22 is available here without any problem. I can, because after deleting 22 still there is one more key available, that is 35, which is in this bucket and which is pointed by this left hand child pointer of this particular node, which has only one key, hence there is no problem. After deleting that, this is going to be the shape of the B plus tree. This is the final tree after deleting 56 and then 42. This is how we can perform insertions and then deletions on the B plus tree, and every time we need to be careful about the rules that have been specified for the B plus tree. Now we will have a look at an example which will describe us how to design the node structure for a B plus tree. The specifications are like this. We need to design a B plus tree indexing for student relation. That means there is a file which stores student records. On the student ID, that is, what is the indexing attribute? It is student ID, which is the key of the relation. The attribute student ID is of 4 bytes length. Other attributes of the table are student age, which is of 4 bytes, student name 20 bytes, student address 40 bytes, and student branch, which takes 3 bytes. The disk block size is equals to 1024, and if the tree pointer takes 4 bytes, the tree pointer, that is, if you look at a tree node here, this pointer requires, which is pointing to the next level node, requires 4 bytes. For the above situation, design the best possible number of pointers per node. That is, I am going to design the structure for the internal node of the B plus tree. And we always, what happens is, if you look at the B plus tree, each internal node or any node is actually captured as a, conceived as a disk block. Okay, so each internal node will be a disk block. Now having this kind of information, let us try to design the internal node of the B plus tree. Disk block, let us have a look at the given information which is useful for designing the structure. Disk block size is equals to 1024. That means disk block size is equals to 1024 means that should be the size of the internal block, internal node of the B plus tree, because each node is going to be accommodated in individual block or disk block. So this is going to be the internal node whose size is 1024. Size of the B plus tree node is equals to size of the disk block. Each tree pointer, if you look at each tree pointer, that takes 4 bytes. And the key, if you look at the B plus tree node, what it contains? It contains pointers and then key values. The key attribute here for this example of student relation is the student ID. What is that? In the previous, it is given as the student ID, which is the key for this relation. Okay. And in a B plus tree node, the number of pointers will be number of keys plus 1, or number of keys is equals to number of pointers minus 1. And assume that since I don't know how many keys can be accommodated there, I assume that the number of keys that can be accommodated in each node, that is each disk block, is equals to n. If I have n number of keys, how many number of pointers can be there? It is exactly n plus 1. Then now if I have, that is, this is the disk block and which is the internal node for the B plus tree, I have n keys and then n plus 1 pointers. That is why the maximum size must be of the block, the size of the block must be equal to or less than this whatever is, that is the total space occupied by n number of keys and the total space occupied by n plus 1 number of pointers must be less than or equal to the size of the block, that is 1024. That is the formula we need to use. Then the minimum size of the node is equals to number of keys into size of each key value, that is n number of keys into size of each key is equals to 4 bytes plus number of pointers. How many pointers can be there? If there are n number of keys, it will be n plus 1 number of pointers. What is the size of each pointer? Again it is going to be the block pointer. Here it is given that the block pointer is going to take 4 bytes, hence it is 4 bytes, n plus 1 into 4. So this is going to be the size of each internal node of the B plus tree, and since each internal node of the B plus tree is going to be fit in a disk block, it must be equal to or less than 1024. And if you solve this equation, 4n plus 4n plus 4 must be less than or equal to 1024, 8n plus 4 must be less than or equal to 1024, and 8n must be less than or equal to 1024 minus 4, which is 1020, and n must be less than or equal to 1020 divided by 8, which is equal to 127.5, or it can be treated as 127. That is why what is this is n, value of n, that is the number of keys that can be accommodated in internal node is equals to 127, and when I have 127 internal keys, then there will be 128, which is one more than the number of keys, that is nothing but the number of pointers which can point to the next level child nodes in the B plus tree. Hence I have 127 keys and then 128 pointers in each internal node, and if you calculate 127 into 4 plus 128 into 4, this will be definitely less than or equal to 1024. Hence this is the best possible situation, that is the best possible situation is I can accommodate 127 keys and then 128 pointers in this B plus tree node. Okay, this is how we can design the internal node structure for a B plus tree. So in this session we discussed what is tree indexing, what is a B tree and B plus tree, what is the basic difference between a B tree and then B plus tree structure. We have seen all the concepts related to B plus trees, that is what is the order of the B plus tree and how a internal node looks like, and what is the leaf node and where we can get the pointers for the actual records in a B plus tree. And in a B plus tree, the pointers for actual records are always found at the leaf level, whereas in the case of B tree it can be at intermediate level also. Then we have seen a few examples which describe as how to design, how to insert records into the B plus tree, and then how to delete keys from the B plus tree. And we have also seen a sample which tells us how to design the best possible structure for a B plus tree internal node given the specifications like disk block size, tree pointer size and key size. And let us stop here. Thank you very much.